Okay, in this question I want to look at an example of a differential equation where we're not using kinematics. It's not referring to acceleration or velocity or displacement. In fact, this one's about Newton's law of cooling, which states that the rate of cooling of a body is proportional to the difference between the temperature of a body and the temperature of its surroundings. So the rate at which it's cooling is proportional to the difference between the temperature of a body and the temperature of its surroundings. If theta is the difference between the temperature of a body and the temperature of its surroundings, then, and actually in this year it gave me the differential equation, but it could quite easily ask me for that. So we're talking about a proportional relationship, which means one variable is some constant times the other. So there's a proportion happening here between the difference between the temperature. Here they're saying theta is that difference, so if I multiply theta by some constant, I will get the rate of cooling, the rate at which theta is changing with respect to time. Also, we're talking about it cooling, which means this will be a decreasing function. Theta will be decreasing, so the rate of change will be negative. As it happens, in the year this came up, they gave you that equation. So a body cools from 80 to 60 in 10 minutes. The temperature of the surroundings is maintained at 20 degrees Celsius. Okay, so a couple of things. Remember, theta is the difference between the temperature of a body and the temperature of its surroundings. So if the body is 80 and its surrounding is 20, well then theta is equal to 60, the difference there. So initially, when t equals 0, theta is equal to the difference between 80 and 20, which will be 60. And when t is equal to 10 minutes, theta is equal to the difference between the temperature of the body and the temperature of its surroundings, which will be 40. So we have a first order differential equation. d theta dt is going to equal to negative k times theta. I want to solve this thing. I want to find ultimately the value of k. I'm going to do what I do all the time. I'm going to separate and then integrate, dividing on both sides by theta and multiplying on both sides by dt, and then taking the antiderivative on the left, taking the antiderivative on the right. The antiderivative of 1 over theta with respect to theta is the natural log of the absolute value of theta. Now here, as the body cools from a higher temperature to 20, the difference between the temperature of the body and the temperature of the surroundings is always going to be positive, so I don't really need my absolute value brackets in this case, as the natural log of theta is going to be equal to negative kt plus the constant of integration c. Okay, so there's my general solution. I suppose I want to solve this. And first of all, I'm going to find the value for c, then I'm going to find the value for k. Okay, so what are we told? I'm going to go back to my conditions on my question. It says when t is equal to 0, theta is equal to 60. So theta is equal to 60 when t is equal to 0. So solving that equation, we get the natural log of 60 is equal to negative k times 0. That's just 0, so that's c. So my particular solution here, in terms of k still, natural log of theta is going to be negative k multiplied by whatever t is, plus the natural log of 60. Okay? And again, I might just get kt on the left. Let's try this one more time. I'm going to get kt on the left, adding kt on both sides, subtracting the natural log of theta from both sides. And if you know your rules for logs, natural log of 60 minus the natural log of theta, well, that's going to be natural log of 60 over theta. So there's kt in terms of theta. Also, we're told that, going back to my initial conditions, that theta is equal to 40 when t is equal to 10. So theta is equal to 40 when t is equal to 10, and we're going to start solving here. So substituting in, therefore t is 10, we're going to get 10k is equal to natural log of 60 over theta, which we're saying is 40. That's of course the natural log of 3 over 2, or 1.5 if you prefer. So dividing on both sides by 10, k is equal to the natural log of 3 over 2, all divided by 10. Okay, and that's the first part of the question. It says find the value of k. So the value of k is that value there. That's what k is. The second part says, the second part of the question says find the temperature of the body after a further 15 minutes. So 10 minutes has passed, a further 15 minutes will make the total time 25 minutes. So when t is equal to 25, we're trying to find the temperature. So what I'm going to do is I'm going to go back to my, so we're now into the second part, I'm going to go back to my kind of particular solution. We have a value for k. I'm going to substitute it in here. So we're going to get k, which is the natural log of 3 over 2 divided by 10 multiplied by t. That's equal to the natural log of 60 over theta. Okay, so I've just plugged in my value for k here. We're trying to find theta when t is equal to 25. So we're trying to find theta when t is equal to 25. That's our goal. Okay, so I'm going to start by substituting in. So when t is equal to 25, the natural log of 3 over 2 over 10 multiplied by t, which is 25, will be the natural log of 60 over theta. So I have to be really good at my rules of exponents here and understanding logs. I've got to know all this stuff. 25 divided by 10, that's just going to be 2.5 times the natural log of 3 over 2. I'm just going to start writing that as 1.5 just because it's going to be a little bit easier. And that's equal to the natural log of 60 over theta. Remember, natural log is a log base e. Okay, so this thing on the left, 2.5 times the natural log of 1.5, is the exponent to which e is raised in order to get 60 over theta. Okay, so being able to convert that logarithmic equation into this exponential equation, really important. And again, if you just think of that as over 1 and use a bit of cross multiplication, I suppose multiplying on both sides by theta will give me theta over here. Dividing on both sides by this e to the power of 2.5 natural log of 1.5 will give me 60 over e to the power of 2.5 times the natural log of 1.5. And you can plug that into your calculator. You can plug it exactly as it is. You should get an answer from there. So let me just do that on my calculator. I'm going to get 60 over e to the power of 2.5 times the natural log of 1.5, and my answer is going to be 21.77 degrees Celsius. Okay, so there's my value after 25 minutes. That's going to be my temperature. Okay, so there's an example of a differential equation that is non-kinematic. It's not to do with acceleration, velocity, displacement, those kind of things. Fairly straightforward, very kind. They gave me the actual first order differential equation, so it was just up to me to do the rest. But I solved them in a similar way to what I do all of them. Make sure you're always keeping in mind what you're looking for at the end. Keep an eye on the prize. Okay? So practice, practice, practice.